Um, so hello everyone. This is my week 8 presentation, and this is problem 5.5.7 in the textbook. And the problem is as follows. So by the tree method, I will prove that the following four ways of saying that the president is squeezy are logically equivalent. And it says here, note that it's enough to test validity of a cycle of four arguments, meaning that if I will do a cycle of if then statements with of statements such that the other statement is the conclusion, then I will be able to prove all of them. So for example, if I were to prove A to B, B to C, C and D, and A and D and A as logically equivalent, then I have basically proven that all of this that these four statements are valid, are logical equivalent rather. However, I had trouble going that route. So instead, I found an alternative. I instead went from B to A to D, D to C, and from C to B. So with that in mind, let's get started to my trees. Although they don't put trees in here. Anyway, so first of all, from B to A. So I have here B as my premise and A here as the conclusion. So as with any tree, we start with with those as our premises, and then the denial of the conclusion. Okay, so so statement one is the premise, and statement two is the denial of the conclusion. I just jump to that. Statement three here is the composition of statement number two. Since since it is the denial, since statement two is the denial of the consequence of the conclusion rather, and so basically we will negate this whole thing. And how I did is that so this existential becomes a universal quantifier. The the contents of the existential quantifier is also negated, though the wedge becomes the conjunction becomes a disjunction, and vice versa. The the existentials becomes the universal quantifiers rather become existential quantifiers, and then its contents are negated, and that is basically statement number two. Sentences 4 and 5 is stems from statement one. Since statement one is a conjunction of two statements, I just regarding the truth tree, I just decompose them in that order. So with statement number 4 being the one part of statement number 1, and sentence number 5 the other. And here this is will and here I labeled this as 6A and 6B because this is the first major branch of the tree. And this comes rather with the composition of sentence number 3. Since we have a conjunction here, the tree will branch off into two parts, with one part having having this statement rather, which can be seen here, and another branch having this branch, which is here. And since it's gonna be very tricky, so we will have to focus on one branch first. Okay, so we're gonna start with the left part. So that is currently sentence 6A. We're gonna disregard A, so we're just gonna say that there's gonna be okay. Sentence 7 of the left side stems from sentence number 5 in the original branch, in the major trunk of the tree. And since there was an existential quantifier in the first part, we first denoted an existential quantifier for that, and I chose that x will be represented here by a. So everything that x encompasses becomes a in here. And statement 8a is just me choosing my value for y here as a because it's an existential quantifier. I have to choose an existing variable from the already named variables, and a is the only one I have named so far. So we have here as this sentence, which is the result of 7a of, of sentence 7, and sentence 9 here is just me naming a again for this sentence for sentence 6. And it says here that for all x, the statement p and x negated, px and qx negated. And since x is I call my x as a, we will have not pa and qa. And sentence 10 here is arose from sentence number 4 here. Since again, a is the only variable that I have currently named, everything will be a. And why I did this setup instead of decomposing some of the instead why I did some of this is instead of decomposing is so that the branches will not be as tricky as the other ones, because I will have to split and merge cells that much, and this, as you can see, this will be the result, so I have to resort to this. Okay, moving on. So here we have a okay. So the preceding one, 11, sentence 11, there is again another branch here. This branch will again branch, and this is basically the composition of sentence 9. Since it is a negation of a conjunction, it will result to a disjunction, and our branch and it will result in the negation of the two of its parts. So we will have negative not PA here and not QA. And then in here, so as we currently have two parts now, what I then did is that for sentence 12, I applied this sentence PA if PA QA, and applied it to all of the branches. So we resulted in 3 branches total. And since the and for a okay, and for for an if then statement, or for an if then statement, for it to be true, we will have the negation of the consequent, and the I think I mixed up the two parts, but never mind that. We'll have the negation of this one, and then the affirmation of this one, and that is can be seen here. And here, one of the branches closes in here, because one of the branches here close because there will be a contradiction in the path. So not QA here, and then in here we will have QA. So this one closes. And then, so since we have 3 paths here, and then we're now gonna pull off this one, this biconditional here, PA if and only if A is equal to A. And for that to be true, then PA, and these are the only 2 choices which will be applied to each of the other remaining branches, such that PA is equal to PA, and such that this one here will be true, and this one also here will be true, or both of them are false. So if this one is also both parts are true and both parts are false, that will be the only case where that will be true. And for this branch right here, we see that since it calls that PA, and but we have not PA here, so this branch will close. And for this one, we will have A is equal to A, not PA, and then not A is equal to A. Now, this statement right here is usually a contradiction in itself, since this one is an identity rule. If you are not equal to yourself, then what are you? That's basically saying it. So that will be a contradiction. So naturally, it will close. And since that will result in every tree, PA is not equal to QA, every tree that has that notation, not A is equal to A, will close. So for this one here, and for this one here too. And 1, 2, 3. Yeah, we should disregard this one. Yeah, disregard this. And then for this branch here, since we have also a PA, so that will be a contradiction. And also that's that notation again. And it will also be for this branch too. PA is not A equal to A, not PA, and then not A is equal to A. And the first branch here will then dissolve. So we will move on to the second branch. And for this one, we first started with statement 3 here. Yeah, so as a result of statement 3, we divided the tree into 2 initially, and this here is the segment that will be devoted to this branch. And then what I did here is for statement 6 is that for your statement 7, 8, and 9 is that I decomposed it into 3 parts, since it is I decomposed it into 3 to make it easier. So again, this is a negation of okay. So first what I did is that I first I first assigned values for x and y. And since we haven't assigned yet values here, so I assigned x as A and B as B and y as B. And then since this is a negation of the consequence of an if then statement, we'll then have our for it to be false, we'll have our first part as true and our second part as false. So with this one as true, Px and Py, we'll have Pa and Pb, since we have denoted that A and B as x and y. And then since n, and that will be the result of that. Since x. And then in here, PAQA as again as a result of statement number 4. And then we are going to decompose this statement, which resulted as in not PA and no, there's a missing part here, I think. Hmm. And P, not PA, and this should be QA only. Yeah, there we go. Still makes sense. Yep, it still makes sense. So again, I decompose this statement. So we'll have not PA and QA because that is. And in here, since we have not PA here and then PA here, this branch will close off, and we will then continue with this path. And for this, I then this is a result of statement number 5. Since again it's an existential quantifier, and we have already named variables A and B. We'll have to name a new one. So I named here C. And statement 13 is a result of statement 12 with Y as A. And then statement 14 is just doing the biconditional. So for a biconditional, again, to be true, we'll have both parts true or both parts false. So we will result to PA and A equal to C, and another branch as not PA and not A is not equal to C. And for this path, since we have PA there already and we have not PA here, there will be a contradiction. So this path will close. And in here, this statement will then continue on to statement number 16. And again, this is PB if and only if B is equal to C is a result of statement number 13. And that will result into again another two branches with PB and PC, and not PB and not PC and not BC equal to C. And this path will close because we have PB already in here. And if we will have not PB here, there will be a contradiction. So this path will close. And in here, with the implication that P is equal to C and A is equal to C, then we can say that A is equal to B. By doing so, we will have a contradiction here. Since we have not A is equal to B, then we will have A and we have A is equal to B. Then that cannot be, because what will be then the implication here is that if A is equal to B and not A is equal to B, then and then B is not equal to B. So that branch will close. And that is step this and that is my work from B to A on towards A to D with with the with the former conclusion now as the premise, this one, and the and statement D, which is this one as the conclusion. So in here, those are our sentences 1 and 2. Sentence 3 here is just me simplifying number 3 further by applying the negation towards the by applying the negation to everything. Statement 4 here is a decomposition of statement 4 and yeah. Statement 3 here is the composition of 2. And statement 4 here, since it is a conjunction, I just decomposed it into two smaller parts, so it will be much easier to read. And we will have here as this statement as a result of this one. And again, this 2. And then statement 6 is just me using this existential quantifier to its fullest. So since there exists an x such that px and qx, and so I will name x as a in here, and then we'll have pa and qa. And statement 7, 8, and 8 is a decomposition of number 6, since this is a conjunction. Statement number 9 is a choosing of a variable in here for number 9. Or statement number 3. So every x here turned into an a, such as for this one, qx then becomes qa, and then this x here becomes an a. And then statement number 10 is, since it is a disjunction, I will have to cut off the branch into 2. So we will have not qa here, and then this part right here. However, since not qa will close the branch instead of the other loop, since we already have qa here. So we will have this branch here, and then this branch as the continuity. So on we go to statement 10b. Statement 11 as a result of statement 10b will have pb if and only if b is equal to a. So again, this is an existential quantifier, so I name my y as b. So since we have to name a new variable, and every y then becomes a b in this one. And since it is a negation of a biconditional, for it to be false, the then one of them must be false. One of them at most must be false. So it's either PB can be true or PA is equal to false, or not, or P is not equal to A, or not PB and P is equal to A. And so let's start in here first with the right path in here. 12b. So as the result of decomposing the biconditional, another path will be not PB and then B is equal to A. And then since B is equal to A, then we can say that PB can also be equal to PA as a result of statement 13b and statement 12b. However, if we name not PA, then one of the branches will close since we already have statement 7 as PA. So this branch will close. Then on to the next one. So we have here PB and not PB is equal to A as a result of the biconditional. And then statement 14a will be it's just me naming a variable for statement number 5. So I chose X as A and Y as B in here, then replace accordingly. As you can see, Px, Py, if X is equal to Px and Py, if Px and Py, then X is equal to Y. So if PA and PB, then A is equal to B. Then again, since this is a conditional, we will have to divide this branch into 2 with 15a as the negation of the consequent and A is equal to B as the affirmation of the PA and PB as the negation of the consequent and A is equal to B as the affirmation of the antecedent. There we go. And then this one will fail automatically because since we have A is equal to B, but when we already have not B is equal to A here, since that means that if A is equal to B, then we can write here as not B is equal to B, and that again is another contradiction in itself. So this path will close. For the other path, not PA and not PB, that will branch off into 2 parts, which will result in not PA and not PB. And those branches will fail because we already have PA as sentence number 7 and PB as sentence number 12a. And that closes the second part of my work. And this is one, D to C. So again, our conclusion again now is our conclusion is now the premise, and then we will add this statement here, and or its denial rather, and those are our 2 premises. So statement number 3 is just me decomposing statement number 2 by applying the negation. Yeah, I should. This is much better. Yeah, parentheses will be much clearer if written in this way because yep. I think I will also apply that one to the last one too. Okay, moving on. So this negation right here will then be applied to everything. So existential becomes universal. Disjunctions become conjunctions. Conjunctions become disjunctions, and then it's every content is then negated. There we go. And then statement number 4. Oh, okay. So for this one, I just did a little backtrack first. So instead of applying everything at once, I first applied it to the existential quantifier before applying everything else. Statement number 4 will be me applying it to everything else. Statement number 5 here is me naming an existential quantifier x as A. And since we have a conjunction here, so we'll decompose this one. And by decomposing, we'll have to add a check here. And so it will result into 2 parts of a path, so which will be QA and then this statement right here, which encompasses an existential quantifier and a biconditional. Statement 8 then is the result of statement number 4. since this is a existential quantifier applied to a whole sentence, oops, and a as our only sentence in here, we'll have to name a in everywhere. We'll have to replace x with a in the statement everywhere, and then remove the existential quantifier. Where was I? In here. So as you can see, x in here becomes a, x's in here become a in this part. And then statement number 9. Since statement number 9 in here is the result of decomposing statement number 8, see that statement number 8 here is a disjunction with 3 parts, meaning the branch, meaning that this branch here will decompose into 3. Is a disjunction of 3 statements, meaning this statement right here will decompose into 3 parts. Okay. So statement 9a will have this one. For the middle one, we will have not QA. And since you have not QA here and then QA in statement number 6, then this branch will close. And then this statement right here, which is, we will call 9C. And we will start here with the left branch first because that one will close relatively early. So since we have not P in here, then we will have a biconditional in here. Oh, okay. So with 10A here, with 9A in here rather, we will then move on to statement number 10, which is me using of statement number 7. Again, we have only named a as our variable so far, so we will have to use this in our statement, replacing y with a in here. So we'll have this by conditional PA if and only if a is equal to a. And that will again result in 2 parts with both parts true and or both parts false. If both parts are true, then we will have PA here. But since we have statement 9a as PA as not PA, then that branch will close. The same is true in here with both parts false. But then again, we have here as a is not equal to a. As I have said before, that is a contradiction in itself, since every some due to the failure of the identity rule, and this one is a contradiction, so that path will close. So we are done with branch 9, with the first branch. The second branch closed relatively early, so now we are down to the third branch. Okay. So this one is the third branch, and then similarly to statement number 10 on the other branch that did not end earlier, we also apply the biconditional here. How? And similarly to the second branch here, the second branch with both parts false will also end prematurely. And so we will go we will continue with the branch with both parts true. Statement number 13 here will then be an application of statement number 9 here. And we have to name a new quantifier for this one since it is an existential quantifier. And I name y as b. So every y in this prior statement will become b. And since this is a negation of a conditional, so we will have the antecedent true and the consequent false. There we go. And since we have decompose statement number 13, we will have to put a check one. Statement number 16 Statement number 16 is an application of statement number 7 right here. Instead of using a again here, we will instead use b for y. So every y in this statement will become b. So PB, if and only if B is equal to A, and since it's a biconditional, one part will be both parts true, or in both parts and both one part is both parts false. With both parts true, we'll have B is equal to A. But since we have statement 15 here, which says not B is equal to A, meaning these two statements will contradict with each other. Therefore, this path will close. And for statement number 7, and for the other part, we have not PB and not B is equal to A. However, we already have PB in here, meaning this path will also close. So that is our third statement done. And lastly, which is C to B. So again, our first statement will be will start with our earlier conclusion, now the premise, and then the first C to B, which was the conclusion to the other one. Oh no, which was the premise of the first one, will now be the conclusion. And those are our premises. Statement number 3 is again a decomposition of the denial of the conclusion. I applied here I applied every negation to every part. Negate, reverse the quantifiers, disjunctions become conjunctions become disjunctions, and then negate the contents. Statement number 4 is oops, there we go. As you can see, as I was talking about earlier, I negated everything from the quantifiers to the parts. Statement number 4 here is me naming an is me getting rid of the existential quantifier with x being a. So every x in the statement will then be a. So we'll have PA and QA, and for all y such that PY such that if PY if y is equal such that y is equal to a if PY. And so since number 5 is a conjunction, oh no, statement number 4 is a conjunction, we'll have to bring these three parts down. So this one right here as with a statement number 5, this QA here as statement 6. Oops, that's my whole name right there. and state and the third one as statement number 7. Ooh. Then okay, I see what I did here. Then this should be not 7. And for this one, what I did next, which resulted in the branch of A, which resulted into a which resulted the tree, which split the tree into two rather, is that I divided this statement number 3, and since we divided that, we should put a check here. So with this part for statement 8a, and this part as statement 8b. And we will first begin with the second part here. So first, with 8a, we are going to make use of b. Since it's an existential quantifier and we already have named a prior, so we will have to use b. So every x in here will become b, and this will result in not b, p, and in the negation of this conditional. And with the negation of the conditional, we will have the first part true and the consequent false. And statement of A here is a result of statement number 7. Since we have named a P prior, we are going to use now P for statement number 7. So every y in here will be P, will be B. There we go. And since this is a conditional, this tree will then split into two. So we'll have not B, not PB or B is equal to A. Now, if you have not PB here, then this branch will close, since we have PB already in statement number 10. And so we are left with this one, B is equal to A. And with B is equal to A, then we can basically name um, QA here. So then we can name here QB, because if B is equal to A, then this one right here, QA, can be QB. And that will result in a contradiction, because we have already named, since we already have not QB in the tree. And on now to the next part. So we have this one as a result of the statement number 3. And for 8b, we have to first name a new variable, because we will have to get rid of the existential quantifier. So every x in here becomes b, and since this is a negation of a biconditional, then for it to be false, one of its parts should be false. So in here, the first part true, the second part false. In here, the second part false, the first part false, and the second part true. So we go first to the latter. So we name here not PB, and then B is equal to A. With the implication of B is equal to A, then this PA right here can be a PB. However, since we have PB in here, and that means it will result in a contradiction, and this path right here will close. And now we go onwards here. As I've said earlier, this one results with the first part true and the second part false. Wait, something's missing. No. And then what I did here is that I applied statement number 7 to this part. And since this is a universal quantifier, we can use B here, and I do so. So BB is not if PB, then BA, then B is equal to A, and that will result in not PP or B is equal to A. Now, since we have resulted in not PB in here, then this path will close. And since we have P is equal to A here, then this path will also close, since we have not P is equal to A in this part. So with both path closing, we already have closed trees, and that is already the from C to B. So we have made a full revolution on the statements, meaning that all of the statements are logically equivalent to each other. And this one here is De Morgan's law. I just wrote this so it will be very easy to write some of the negations very fast. And that is it for my presentation. That's it's very long, because the problem really is very long. So thank you for bearing with me here, and we'll see you in the next one.